Mm. Right. So we change tracks slightly today. Uh, what remains a sort of invariant for the course is the fact that we will always be dealing, always meaning more than 90% of the time, with ideal gases. So ideal gases will remain in focus almost all through. Occasionally will, as I said, less than, much less than probably 10% of the course, will step out of the ideal gas routine and talk about a little bit of interaction between the particles and how it changes the pressure, temperature, volume relationship. But apart from that, this is essentially a course on ideal gases. We looked at one aspect of the ideal gas over the last few days. And now we are in the process of starting to look at another aspect of the ideal gas. Namely, we ask the question, what can the ideal gas do for you? So there is this container full of, let's say, an ideal gas. And the issue is that what is it that I can expect from this ideal container full of ideal gas? So here is my ideal gas over here in this container. And now the first thing that an ideal gas can do for me is that it can do some work. For example, if I were to have a movable piston which is enclosing this ideal gas and heat it from below, then heating this ideal gas pushes up the piston. There are two effects. One, gas becomes hotter. Two, gas pushes out the piston. So the point is that I can use the ideal gas to get some work done. And I can also do this to store some energy to be used later. So the hot gas can be later used to, can be used as a store of energy, which I can make some good use of at some later time. So primarily, I mean, it has some internal energy which I can manipulate. Internal energy is what you are familiar with, the energy, collective energy of these single particles running around, and their kinetic energy, total kinetic energy, is what amounts to the energy of the energy of the gas. And so there is that energy store which you can make use of, and one of the primary uses that you can make of it is this get it to do some work. So this part of it, which so the business is that of thermodynamics, the two parts relating to the two essential characteristics of an ideal gas, the thermo talking about the fact that it can, there is give it a certain amount of heat, the gas its internal energy would increase, and you have a ready source of energy which you can use, and you can use it to push out a piston and get some work done. So that's the dynamics part of it. And so for the next few days, our focus would be on this very often the ideal essentially systems which are where doing some work and providing heat go hand in hand. And for our discussions on specific systems, most of them would feature the ideal gas, but there would be some other systems which are sort of equivalent to the ideal gas, which one should keep in mind. And then there are the real systems which is the working with the real gas, which can be slightly different and can produce some effects, which some fine points, some finer effects, which the ideal gas does not have. So a little bit of that at the appropriate time, but for the most part, it's going to be essentially.
So some people are waiting.
So for essentially, it would be a discussion on ideal gas as a working substance. So that's that. Now, in the process of doing this, I'll need a couple of math issues, which is best to get out of the way. There is a high chance that you know them very well already. There is some chance that maybe you have seen it slightly differently, more formally, and so on and so forth. So let's, to keep all that sort of make it all irrelevant, let me do a couple of things which I will need along the way, so then one does not need to stop and work it out. So the first few minutes I will talk about function of two variables, so there are some standard trivial properties, and then go over and then look at it slightly from the backward direction, which you will see what I mean by that. And then we are ready to go ahead and tackle the actual thermodynamics which we will be dealing with. All right. So the maths that I need to know is essentially a function. What happens to functions of few variables, let's say x, y, z, and so on. We'll focus on just two. That's going to be these things are pretty bad, but two, focusing on two is not really running away from the fight, sort of, because the ideal gas that we are going to deal with, there you have an equation of state. The pressure, given the volume and temperature, we know what the pressure is. So P is some function of V and T. So that is very often the situation that we will be in, that given it's the thing which we are interested in would very often be a function of two variables. And so three or more are possible, but certainly we will not be handling it in this course. And also, it is far more difficult. Handling a function of three variables is somewhat more complicated than handling two. Two is straightforward, and we will just need to know what the basic business of this is.
Someone is waiting. Can you please let him in?
So my interest is going to be in a situation where it is z is a function of x and y. So long, just as p equal to some function of b and t, and the prototype that we will be talking about is z equal to some function of x and y. So z equal to some function of x and y, and you know immediately that dz, the differential, can be written as del f del x dx plus del f del y dy. These notations are partial derivatives, where del f del x means that it is limit delta x tending to 0 f x plus delta x y minus f x y divided by delta x. That is partial derivative of f with respect to x. Similarly, del f del y is limit del y tending to 0 f x y plus delta y minus f x y divided by delta y. So, and nothing problematic there. We will restrict things to situations where the derivative del to f del xy is equal to del to f del yx. So we will be working with the situation. Primarily, we will be working with situations where this result holds, that the derivative dz, z can be written as f of xy, dz is equal to this, and therefore this partial. This, however, may not always be. If this does not happen, then life is a bit more complicated. That is, if you give me a function of two variables, z equal to f of xy, then I can write this, and all analytic functions that we get are going to have this property that if I take a derivative with, if I change the order of derivative, when I talk about the second derivative, there are three kinds of second derivatives. There is del to f del x squared, there is del to f del y squared, and then there is the mixed derivative, which is once with respect to y and one. And the ordering for one restricts oneself generally to functions where the ordering does. So nice analytic functions where this ordering does not count, and you have you can make use of this relation. So that's your a function of two variables. If I give you z equal to f of x y, where f is a well-behaved function of x and y, then the definition of del f del x is this, definition of del f del y is this. You can use these as functions to define their derivatives. You get this, and you get this and this, and these two are, that is, whether you take delta x going to 0 first, or whether you take delta y going to 0, or you take delta y going to 0 first, does not matter. So this is so that's the function of two variables if I give you z equal to f of x1. But suppose I don't. This part is straightforward. But suppose I don't give you z equal to f of xy, but I give you dz is equal to f1 of xy dx plus f2 of xy dy. So that, let's say, is all that I give you. And I ask you whether I ask you to give me from here, starting from here, give me z equal to f of xy. Now your life is going to be extremely complicated, because if dz is not of the form, this z equal to f of xy over here told me that dz is equal to del f del x dx plus del f del y dy. So that from this follows. If f of xy is a nicely behaved function and I don't have problems with the derivatives. But now I'm asking you a reverse question. I have told you that dz is equal to this plus this. Can you give me this function f of xy? So given this information, so get this very clearly, because this is the maths that one would be encountering. That given this situation, can I get this? That is the problem. Well, if now you argue that if this, then this. If z is equal to f of xy, then dz is equal to this. All right? So dz equal to del f dx, and then you will tell me that if this thing over here has this structure over here, then I'm in business. I can tell you from this relationship what this is. And when do you know that this and this are the same? If del f1 del y is equal to del f2 del x, because f1 would have to have the form del f del x, and f2 would have to have the form del f del y, and that is ensured that if del f1 del y is equal to del f2 del x. So if over here, if the dz that I have given you has the property that del f1 del y is equal to del f2 del x, then it is possible for you to give me a z equal to f of xy, which is this. So you see, but suppose it's not. Suppose I give you a nasty dz where this is not satisfied. Then you can't give me z equal to f of xy. So you see, you have, as soon as you entered the domain of function of two variables, I'm going to have a difficulty. I mean, this difficulty, I'm not really interested in the maths and the difficulty of the maths, but I'm interested in thermodynamics, and my focus on this is entirely just the part which is relevant for it. I'm going to talk about things like pressure, volume, and temperature, and P is equal to some function of V, and T is going to be my equation of state. And I have given you some relation, which is a relation among differentials. If I give you a relation among differentials, can you, which is what we will be encountering very soon, then if I give you a relation between differentials, can you give me the function? That is, I give you only the relation between dp, dv, and dt. Would it be possible for you? I mean, there some function exists in this particular case, but I mean, the function, the dp, would, I mean, you know that P is equal to, let's say, ideal gas, RT over V. You can write down a dp which looks like this in terms of dt and dv over here. Great. And they have the property that these derivatives are the second derivatives work. But suppose I don't know the equation of state, and I only give you this relation over here. Suppose that were to happen, that the dp were prescribed as some function of this v and t times dv, and then some function of v and t times dt. And I asked you to go and find me the pressure. Well, you would carry out this check over here. And if it works, you will say, aha, I can get you the pressure very trivially, because this is true and I can figure out what the pressure is. But suppose it were not true. Suppose I gave you something where this did not work out. Now you are stuck. So this is the situation which one wants, that I give you this relation between differentials. Given a relation between differentials, can you come up with a relation which says that the standard forms where, I mean, a differential for which this is not valid anymore? So I give you, say, a situation with a differential where this is no longer true. In that case, what are you going to do to this differential in order that this may become true? That is the question. So with this function of two variables, So long as this is work, your dz is this and this works, life is perfect. But the moment you have a dz where this does not work, I give you only dz, that is all that you know. I have prescribed dz in this form over here, and this is not valid. This does not hold. Then what are you going to do? That is the question. So, all right. This is what one has to handle. This is the single new information that you need to have, and thereafter we can go to work. So, all right. So, what do I do? I'm given that, let's say, some df is a function of some df is equal to some a function. So the variables are, let's say, x1 and x2, which is written in this form. You can easily think of adding other variables and talking about it. So df is equal to what you are given is df is equal to some function g1 of x1, x2, dx1 plus some function g2 of x1, x2 and dx2. So this is all that you are given. You are given the relationship that df is equal to this one plus this one. And you find that del g1 del x2, del g1 del x2 is not the same as del g2 del x1. So you are not in business of writing this as a, so what are you, how do you go about this situation? So what you do is that you look at consider the differential equation where dx2 dx1 is equal to minus g1 divided by g2. So I want to consider the differential equation, which is dx2 dx1, the derivative of x2 with respect to x1 is given to me as minus g1 by g2. So I will look at the differential equation given by this. So this particular differential equation. So calling x2, and it is like saying that I'm given dy dx equal to some function of x and y. So that's what this is. So x2 is my y, x1 is this, and dx2 dx1 is minus g1 g2. I'm going to look at solutions of this. So, all right. Given a differential equation, you are going to find it's a first order differential equation, and therefore you will be able to find some solution. You can always solve this first order differential equation and write y is equal to some g of x and there would be one integration constant. So let's say that integration constant is C. So I keep that label C over here, and y is equal to GC over X is the solution with integration constant, which is C. So you are going to, that's what the standard literature tells you, that if I give you a differential equation dy dx equal to some function of x and y, it's a first order differential equation. Integration will get you one integration constant. So, it is, the answer is going to be y equal to gc of x, where c is. So that's technically, that is always true, that you can, given this dy dx, you can formally write down a solution which is y. Or, I mean, which is, which may not explicitly come out always in that form. That is, you can, this explicit writing may not be possible, but you would be able to always write g of x and y, some function g of x and y equal to some constant. That would always be doable. So dy dx equal to f of xy. A solution would mean that you would think that you write y equal to gcx as the g, some g with a constant c somewhere playing, but that may not be always possible. That, for example, I mean, y may come, I mean, this f of xy may be such that y always enters with in combination with x or with some higher power, and so on and so forth. So this is not always, but g of xy, some g of xy, or let's call it some u of, call this g some u of xy equal to constant is always true. So dy dx equal to f of xy, its solution, ideally you would write it as y equal to g of x with some constant c, which is the constant of integration. But that may not always work out. I mean, it may not be possible. It may not simply be a linear thing in y. And and the x and y can get awfully mixed. So, I mean, the thing is that always it's a function of x and y, which is equal to some constant. That form is assured. U of xy is equal to constant. That would be the solution of this differential equation over here. So very good. So there is, my claim then is that some u of x1, x2 equal to some constant c is the form of this solution over here. Fine. So what do they stand for? So you have this x in the, here is x1, here is x2, and this is, let's say, the u-axis. U x1, x2 equal to constant is a surface
Someone got disconnected. Can you let him in?
what? Oh. So what this is, u x1, x2 equal to constant is some kind of a surface in this three-dimensional space of u x1 and x2. So u x1, x2 equal to constant is this surface. if I move along this surface, so so this is my differential equation. This is the solution. So all right, I will move along the surface where along one of these, I mean, pick a particular value of C, and I want to move along this surface. And if I do move along that surface, then it is moving along the surface du dx1 is equal to 0. Because if I move on the surface, moving on this surface over here, it's u equal to constant. So u equal to constant on this surface where I'm moving. So if I change the x1 along this surface, the same holds for x2, that if I change x1 along this surface, you are going to get no change in du. So du dx1 is equal to 0 if I move along the surface, which is the solution of this equation over here. But what is du dx1? That is going to be, so here is my, u is a function of x1 and x2, and therefore I can write du dx1 as del u del x1. So this du, all right, let me write it out, that du is equal to del u del x1 dx1 plus del u del y1 dy1. Dx2 dx2. So du is del u del x1 dx1, that's this. So du dx1, how much does u change as I change x1 along the surface? It is du dx1 is del u del x1, that's a partial derivative with x2 constant, plus it is going to be del u del x2 dx2 dx1. But you know what dx2 dx1 is. Dx2 by dx1 is minus g2 by g1. So this is equal to del u del x1 minus dx2 dx1 is g1 minus g1 by g2 minus g1 by g2 del u del x2. So if I move along this surface over here, I pick up this, so this is the solution surface. On this solution surface, what I get is that du dx1, which is 0 by definition, del u del x1 del u del x1 times g2 is equal to del u del x2 times g1. And I'm going to define a function f, capital F, by this g1 g2 e to the power minus f. So del u1 del u del x1 g2 is equal to del u del x2 g1, which I'm going to call g1 g2 e to the power minus f. So g1 g2 is an e to the power minus f, and this e to the power minus f, this factor that I have put in over here, is has an interesting property that it makes your df that I started out with So, what did I do? I considered a solution of your differential equation, which is this differential equation So I took this differential equation, considered a solution of it, which is u x1 x2. Then out of this u x1, this was a solution. The solution has the property that your del u x1 g2 is equal to del u x2 g1, and that I have defined as g1 g2 e to the power minus f. So now I'm going to go back and I'm going to take this df, and I have this g1 which is so this, I go back to this GF over here, and then I look at the G1. The G1, if I connect this with this, G1 is equal to, G1 is writable as e to the power f del u del x1, and then it is dx1 plus G2. G2 I'll get from this connection here, and that is e to the power f once again, and it is del u del x2 dx2. So df is equal to e to the power f del u del x1 dx1 plus del u del x2 dx2. And this is a perfect differential. So this is equal to e to the power f du. And consequently, df, which was not integrable, df was a differential, but you could not integrate it and write it as f. So there was no f which could be written as whose differential is df. df, that is, given a f, I did not define a df. I did not know the f. I tried to define a function through the differential. So I tried to define a function through the differential. Now this does not, I mean, if this had the property that the derivative, this derivative equals this derivative, then fine, I would have no problem. But I have started out, if I start out with a situation where I need to define the function through a differential, and the coefficients do not have the property, then I play this game that I have shown you over here, and I construct this e to the power f. I find that df is e to the power f, and therefore du, which by construction is a perfect differential, is equal to e to the power minus f df. And so df could not be integrated, but you get this quantity e to the power minus f over here, defined. So e to the power minus f defined by this relation over here, that it is G1 del u del x1 G2 is del u del x2 is equal to G1 G2 e to the power minus f, and you have the answer that this du is now a perfect differential, and while you could not integrate df, you multiply it by this e to the power f, and you have a integral which is there. So del u del x1 G2 equal to del u del x2 G1, and this is G1 G2 e to the power minus f, and it is that e to the power minus f which is the so-called integrating factor. Multiplying by that your df, you pick up this du over here. So this is the basic maths that you need to know. That given this is making this is interesting, and I'm sure you have done functions of several variables in your math courses, so you must have seen it, and therefore, but I need to use it, and I wanted to make sure that we are on the same wavelength, and therefore this is the way I would look at it, that if somebody gives me a function specified only by its differential, you don't give me the function. You give me only what the differential of that function is. And let's say it's a function of two variables to keep life simple. This can be generalized, obviously, to any number of variables. All these generalizations, they are extremely cumbersome and difficult to, at least for somebody like me who would like to work out steps, difficult to demonstrate on a board. So far more complicated. This is easily seen that if I have only two variables and I prescribe a differential for you, I prescribe a function for you, new function, only through the differential. It's something we'll do in a minute. So that's why it's I'm harping on this. Then you may not be able to integrate it. So you may not be able to integrate that differential and really get the physical quantity, which we are after. After all, I took a physical quantity and prescribed it through a differential. Because that is the only way I could define that physical quantity. So I took it, I defined it through a differential, and it took. But now I'm faced with the difficulty that these coefficients do not satisfy this relation over here, and I can't integrate and get a f.
So someone's waiting. Can you please let him in?
Pardon? Here,
someone is waiting.
somebody's wait. So, yeah. So the thing is that I use this trick that out of, if I can't integrate this function, then it's too bad. I mean, progress is virtually impossible. So I find out how to construct a function out of this which is integrable. And what I find is that I can define a f, which I have defined through this relation over here. And that f has the property that this e to the power minus f, when multiplied by df, gives me a perfect differential. So this is the trick for constructing perfect differentials, which is what is it telling you? All right. I mean, I think at this point I can't. No point in giving the example. We'll better do a little bit of physics and then come back to talking about it. Yeah. Are the mathematical steps they are all pretty simple, but is it clear? I mean, because this is something which in thermodynamics one uses a lot. So are you clear? I mean, what I wanted to say is that we will be faced with situations where only a function will be prescribed by differentials, and then whether you can find that function or not is a question which you need to answer. And often you won't be able to find that function because you can't integrate and get but then you need a integrating factor which makes it integrable, and that integrating factor is found from this relation over here. If u is the function which is whose differential would be integrable, then u and f are related by this, and u and the way the integrating factor is defined in terms of the u is through this over here. So this defines the G1 and G2 are given to you. U is what one has to find out, that is this du, and du is related to through du. This du and df are related through this factor over here, which in turn are given by these. So that is what you have got, and that we will see is going to this factor e to the power minus f is what is called integrating factor. So you take your df and all right. So are you comfortable with this? I mean, you have obviously in your thermodynamics, you have done thermodynamics before, so you must have, what actually where one is being driven, but maybe the focus of getting the answer there was slightly different, and this is anyway. I mean, you may have seen, not have seen it before. Maths class must have done it in form which is far more rigorous. This is what I will need, and Are you comfortable with it?
Yes, sir.
Yes,
Yeah.
sir. Yes, sir.
Okay, very good. So let's. So, all right. Now the question, back to the question, what can the ideal gas do for me? So the first obvious thing, I'll get the ideal gas to do some work. So you take the ideal gas in the cylinder over here, heat it, and this is pushed. So, all right, there is this piston which is being, so the area is A, and so that's the situation. The gas is over here. This is a piston, the cross section is A, and the gas pressure, when there is no flame over here, in the absence of the flame, the things are obviously balanced. There is the gravitational, the pressure which that is, the piston is in equilibrium because the mass of the piston is being balanced by the pressure of the gas times the cross-sectional area. That balances the mass, the weight of the piston, and you have equilibrium. So, and now you heat. So this is no heating. Now you heat, and this gas expands. So gas expands, gets hotter, let's put it this way. Gas heats up, gets hotter, pushes the piston out. Now gets hotter. So now what property do I know of the gas from kinetic theory? The gas has internal energy. Which is E equal to 3, something or other. Monoatomic gas 3/2 NKT, NK, let me write it as some alpha times NKT. So, the gas has some internal energy, which is NKT times some factor, which is determined by the precise nature of the gas. So, and this internal energy is going to increase. So, gets hotter means that internal energy increases, pushes the piston out. Pushes the piston out means that it has to do some work. So how much is the work? Work is F times. Work means dW is F times dz. But the F that it pushes out against the cylinder. So this is against the piston. So it's the pressure that you had. So this pressure is times this force which the gas was exerting on the piston now causes the piston to move a little ways up. So P times A times dz over here, but A times dz is dV, so it is pdV. So dW, so it does some work which is dW equal to pdV, and its internal energy changes, so there is some dE. So there's two aspects of this heat which is being supplied to the gas, and that heat which you are supplying to the gas is essentially raising its internal energy by an amount dE and is doing a certain amount of work which is pdV. You use energy conservation in a wider sense. Wider sense meaning that the heat energy is taken into account, the internal energy is taken into account, and taking the energy conservation in this wider sense means that whatever energy came out of here, whatever this so-called heat which was given to the system, if the amount of heat is delta Q, that is the amount of heat energy which has gone into the system, then that has to be equal to the amount of mechanical energy change plus the amount of work done. So just the energy conservation law. Delta Q, that is the amount of energy supplied, which is what you call heat. So because you did it by lighting a flame. So something called heat energy does two things for you: changes the internal energy which you are familiar with from what we have talked about over the last few weeks. So there is an internal energy that you should be comfortable with, and that it pushed out the piston is an observable fact, and therefore there is this, it did some work, force applied, moved the piston up, so some delta W. So delta E plus delta W. So that is the amount of energy that has been sort of, I mean, the gas suddenly finds itself with this amount of extra energy of some kind, some of it which it can recognize as mechanical or thermal energy, and the other, I mean, is sort of a PDV, which, I mean, all right, a mechanical energy. And the total has to have some name because it came from that flame over there. The flame supplied it to, and therefore you call it a heat energy, and conservation laws have to be in force. And so delta Q has to be delta E plus delta W, which ironically is called the first law of thermodynamics, discovered, actually written down, let me be correct, written down 30 years after the second law. So there is a bit of, but this is actually historically these things happen. Newton's first law came, I mean, Newton realized first law long after he had written down the second. So that, I don't know whether you know it or not, but initially the Newton's whole concept, the question of what is non-inertial what is a force-free motion, in a initial idea was that it is the circular motion, and therefore the first law, I mean, he could write down the third law was not a problem. Second law could be written down with the force-free motion as a circular motion. But then, obviously, in his mind, internal inconsistencies. And so the first law actually came that it is the force-free motion, and that came much later. So these things happen. Logically, it has to be the first, second, and third, because the first defines the frame in which the second law holds. So when you look back on history, history has funny things, and which are all right. I mean, shows some light, important because it does throw a light on how people function, how theories are made and developed. But anyway, that's another different issue. Over here, we actually have a very similar thing, that the considerations of heat as being part of the energy process was apparent to Carnot in 1824. And obviously, everything that Carnot wrote down was on the premise that this happens. But the formal writing down was in the 1850s. And so this, what we now today call correctly the first law of thermodynamics, is telling you energy is conserved. Energy is conserved, but in writing down that conservation law, you better take into account the fact that heat is a form of energy. So that's step number one. So dq is equal to delta q is equal to delta w, delta E plus. So there would be dq infinitesimal, it's dq equal to dE plus pdv plus dw, which for the gas is pdv. Very good. So here is, let's get it out. So in terms of infinitesimals, dq is dE plus dW, and for the gas, so that's the general statement. For the gas, dW is pdV, and that is, so any gas, not an ideal gas, any gas, it's pdV. So dq is equal to pdV. And this is where what I was talking about a few minutes ago becomes very important, because Q is something new which you have introduced, and Q has been introduced through a differential. You see, that is why I spent all that time talking about a function which is defined through an differential. I mean, this is the first time one encounters such a strange issue. But I mean, so far as the maths people go, all right. I mean, for them, it is. They would take all these things into consideration. That we are, that's why one needs the maths. I mean, they have the framework in which one can discuss things. But look at the physics business. Over here, I mean, you are doing something which is weird. I can write down, yeah, I know what DE is. I know what E is, which is for this gas some alpha RT for one mole of gas. I understand what PDV is. It is the amount of work that you need to do if you want to push a piston up in the situation in a cylinder. And now the point is that the sum of them defines a new function, which is this dq over here. So you ask, what is q? And if I give you a relation, a p in terms of v and temperature, so E is the same as temperature. So this is like just saying constant into dt. And I tell you that this is I know the equation of state as P equal to RT, 1 mole. So P equal to RT over V. Then, and this DE, this E, let's get the alpha out. It's RT times something, forget, let's put it equal to 1. So DE is R times DT, and this is R over P is equal to RT over V, and you would get dq is equal to r dt plus r t by v dv. So you have, in terms of the differentials, dt and dv, something which is quite, I mean, all right, given to you. But can you give me a q? No, you can't. Because if you take a derivative with respect to v over here, you get 0. If you take a derivative with respect to with respect to t over here, you have something which is non-zero. So this question of writing df equal to del f del t dt plus del f del v dv is gone, because this derivative del to f del v del t is not equal to del to f del t del v. That equality is not there. And therefore, I can't give you what this function f is. So I can't tell you what q is. So q is a strange beast which is defined only through the differential. You cannot integrate it and give me an answer for the ideal gas. And if you can't for the ideal gas, you can imagine that you can't do for anything else in this world. So hence we went through all that. And you know what to do, where obviously you have gone through these things before, and you know what, and but right now you see that I have a problem. So I have a problem, and what does that mean? It means that if I take this ideal gas Now, the one of the ways of so for the ideal gas, showing it has a equation of state as this we wrote down. So P as some function of V and T. So that's the ideal gas you would, or any gas for that matter. You would like to write the equation of state as a function of V and T. So it's good to do things on this. So as a function of, so at a given pressure, if I'm sitting at given pressure, then what does this V and T look like? I mean, in this plot, so what I mean is that the P equal to V of F of V and T, essentially, if you provide the volume and temperature of the gas, you are actually specifying its state completely. Because of this relation over here, specifying V and T specifies the state of the gas. I mean, that is why a function of two variables will be doing so well for us. There are only two independent variables that you can you need to there are only two of them that you can independently tweak. So it is V and T, or you can take your pick. It can be P and V. It can be somebody else. It can be energy and V. But there are only two. There are only two, and therefore it is possible to prescribe the state of the gas on this VT plane. So as soon as I put a point over here in this VT plane, the state of the gas is completely specified. You know what pressure it corresponds to, you know what energy it has, you know what its other attributes, thermodynamic attributes are. And so this V and T is completely specifies the state, and it is a very convenient way of, convenient thing to use. So V and T, so let's say I have this one where it is, this is T1, and this is, let's say, V1. And let's say I do something to the gas, and it goes to this point over here, which is V2, T2. So I have taken the gas done something to it, and taken it from state specified by V1, T1 to a state specified by V2, T2. All right. So now this first question that one needs to ask is, how did I take it there? So how did I take it there? Now, the point is that this relation between V and T, P as a function of V and T, was a relation which came out of, which we got from kinetic theory, PV equal to 2/3 E and E equal to then 3/2 NKT. And kinetic theory, remember, was all about equilibrium. no time dependence at all in anything. It is all, everything is in equilibrium, and the energy that we calculated, the pressure that we calculated, were all for equilibrium situations, things which don't change in time. All right. Now, over here, things have changed. You have gone from, and let's say I prescribe some path and ask you to calculate the work done. So I prescribe a path and want to know the work done, which would be, I thing which you should be able to do. Prescribe a path, ask prescribe a path from V1 T1 to V2 T2 and ask what was work done in going from V1 T1 to V2 T2. How are you going to calculate that work? Things have changed. All that you know, and as I told you that you would have to use dW equal to PdV. That's sensible mechanical work. That's how. But all right, fine. I mean PdV. Now how are you going to calculate it? Well, you say that you are going to use that. Use that. That was in equilibrium. And over here, obviously, you are changing the state of the gas. You are going from one state to another. You are doing something which doesn't look like equilibrium. So how in the world am I going to calculate PDV integral by making use of this over here, prescribing a path and doing it? Prescribe a path, that we have learned, that I have to prescribe a path. Otherwise, I can't do it because it is not this DW is not a perfect differential. So the dW is dq minus dE, and that dq is not. So all right. So this PDV over here, this PDV is I can't use it to calculate. Unless, so to do it, I would have to use this, and then somebody has to also prescribe the path. Just prescribing the path wouldn't take you anywhere unless I also prescribe this. So only then you would be able to integrate PDV and give me the answer. But how can I use this over here, which we discussed in was an equilibrium? So you wiggle out of it by saying that you have taken it from this point to this point so slowly that at every instant the equation of state was valid. So it is P equal to Vt at this point. At next point, you have P1, V1, T1, but it is still P1 equal to F V1, T1 because you waited for an infinite time, so that so you went from here to here, So basically you say that I will calculate by integrating this and making use of this by saying that this transformation took place over a long period of time. Long compared to what? Long compared to what? So there are time scales involved over here. So I think I better stop. Yeah, I have to stop here. But I mean, think about these are the issues which one needs to straighten out before calculation is straightforward. You have done thermodynamics before, so there is hardly anything new that probably I can teach you. But there are issues over here. The process which takes you from here to here is called a quasi-static process. The quasi-static meaning that almost at every point you are in equilibrium, and so that's something, and we'll take it, think about it, and we'll pick it up from there next time. All right. So.